is fz is uxy plus ivxy. What I have written is f bar z, not fz bar, f bar z. So that is f bar z is uxy minus ivxy. We shall see what happens if we write f z bar, but as it is given there, it is f bar z. That means uxy minus I times vxy. So if this is analytic, what happens? So f analytic implies dabba u by dabba x equal to dabba v by dabba y, and dabba u by dabba y is minus dabba v by dabba x. And f bar analytic means what? Dabba u by dabba x is equal to dabba v by dabba y, but v means here minus v. So it is minus dabba v by dabba y, and dabba u by dabba y is minus dabba v by dabba x, but again here minus means minus dabba v by dabba x. So this is plus dabba v by dabba x. So dabba u by dabba x is on one hand dabba v by dabba y, which is minus dabba v by dabba y. So dabba v by dabba y is 0. That means dabba u by dabba x is 0. Similarly, other two are 0. See it here. Dabba u by dabba x is dabba v by dabba y, and dabba u by dabba x is also minus dabba v by dabba. So dabba v by dabba y is minus of that. That means this term is 0. Therefore, this is 0. Similarly here, dabba u by dabba y is minus dabba v by dabba x, but it is also plus dabba v by dabba x. So this is 0, therefore this is 0. So first order partial derivatives are 0, and therefore this is 0. If we write f z bar, then let's see what happens. F z bar. So f analytic fz, and f z bar analytic. That means what happens? So fz is uxy plus I times vxy, and f z bar is what? Now z is x plus iy, then you get xy here. So z bar is x minus iy, means you get ux minus y plus ivx minus y. You may look upon this as a composition, xy goes to x minus y, okay, and z, f of z bar, so z goes to z bar is one function, say suppose g, so this is f composite g. Okay. Now both are analytic means real and imaginary parts of both the functions will satisfy Cauchy-Riemann equations. So dabba u by dabba x is dabba v by dabba y. Now if you call this as capital U, okay, so capital U of xy plus capital V of xy. So dabba capital U by dabba x is dabba capital V by dabba y, but dabba capital U by dabba x will be equal to what? Is dabba u by dabba x, okay, and dabba capital U by dabba capital V by dabba y is what? Dabba u by dabba x equal to dabba v by dabba y. Okay. Now dabba v by dabba y is what? That is dabba u by dabba v by dabba y. On one hand, because f is analytic, and dabba v by dabba y is v is this, Vxy is Vx minus y. So minus dabba V by dabba y. Small v this is. So if these two we want equal, then these two are equal. Dabba V by dabba y is minus dabba V by dabba y. That means it must be 0. So dabba U by dabba x is 0. So dabba V by dabba y is 0. Similarly, if you write other, dabba U by dabba y if you write, then you will get the other two partial derivatives to be 0. So again first order partial derivatives are 0. I want to check this. Dabba U by dabba y is minus dabba U by dabba y. Okay. But that is dabba V by dabba x. And minus dabba V by dabba y is dabba U by dabba. Minus dabba V by dabba x is minus dabba U by dabba y. So you will get 0. Right. All first order partial derivatives are 0. This. So other equations are dabba U by dabba y, but u is small u of x minus y. So it is minus dabba U by dabba y. But that is dabba V by small v by dabba x because of the Cauchy-Riemann equations. Dabba V by dabba y, dabba V by dabba x is dabba V by dabba x. Okay. So that is minus dabba U by dabba y. So dabba U by dabba y is also equal to dabba. So this is all right. This we have already written. Now dabba V by dabba x we want to be equal to minus dabba U by dabba y for u and v to satisfy Cauchy-Riemann equations. So that implies, so this side is dabba V by dabba x and minus of this is plus dabba U by dabba y. So on one hand you get dabba U by dabba y equal to dabba V by dabba x, and on the other hand you get dabba V by dabba x is minus dabba U by dabba. So other two partial derivatives are also 0. So you will get, in that case also, f is constant. Okay. Now let's go to some of the exercises that I have written there. Okay. So I suggest you that you go through the exercises and solve them. All right. Let us see one more important thing in connection with the Cauchy-Riemann equations. That is the harmonic function. Okay. So let us write what harmonic function means. So suppose there is a function of two real variables. Okay. So u xy be a real valued function, be a real valued function of two real variables x and y. And then u is called, so let u be a real valued function, then okay, defined on say D, defined on a domain D, then u is called harmonic, then u is called harmonic function if d2u by dx square, so it must exist. So u has second order partial derivatives and it satisfies that d2u by dx square plus d2u by dy square equal to 0. This equation, okay, is sometimes written like this also. It's called Laplace's equation. operator del is d2 by dx square plus d2 by dy square. It's a partial differential operator, Laplace operator. This is Laplacian. Sometimes it's called Laplacian. So if u satisfies this, then it is called a harmonic function. Okay. Now, what are examples? What are examples of harmonic function? So, you may take u to be, say, x plus y, for example. Okay. So, suppose x plus y, if I take, suppose uxy is x plus y. Then what is dA by u by dA by x? It is 1. DA by v by dA by y, that is also 1. So what is d2u by dx square? That is 0. And d2v by dy square, that is also 0. So trivially this function is harmonic. Okay. So u is harmonic. If I take uxy to be, say, x square plus y square, then what do you get? d2u by dx square. Can you tell me? DA by u by dA by x is 2x, and it's again. Hope you know that what this second order partial derivatives means. This is dA by dA by x of dA by u by dA by x, and this is dA by dA by y of dA by u by dA by y. Okay. So you again find partial derivative with respect to the same variable. That means second order partial derivative. Sometimes you have mixed partial derivative, that is d2u by dx dy. That means dA by u by dA by y, and then you find dA by u by dA by x of that function, like that. So I am sure that you know this second order partial derivatives. So now here it will be 2x and 2, and d2u by dy square is also 2. So d2u by dx square plus d2u by dy square is not equal to 0. So u is not harmonic. So it is not harmonic. But if I just make this y square, if I change to minus y square, so maybe third example is uxy is x square minus y square. Then d2u by dx square is what? 2x, and d2u by dy square is minus, d2u by dx square is 2, and this is minus 2. Therefore, d2u by dx square plus d2u by dy square is 0. Therefore, this function is harmonic. Now, as a consequence of the Cauchy-Riemann equations, we want to observe that the real and imaginary parts of analytic function are harmonic. Okay. So, if we have complex function and suppose it is analytic, then from that we get a pair of harmonic functions. So what I am saying is that suppose if fz is equal to uxy plus ivxy is analytic in D, then u and v are harmonic functions. That means they satisfy Laplace equation. How do we get that? So proof is, we know that if f is analytic, u and v satisfy Cauchy-Riemann equations. So see, we are deriving so many consequences from Cauchy-Riemann equation. So analyticity gives Cauchy-Riemann equations, and from Cauchy-Riemann equations we get lot of information. So now here we get dA by u by dA by x equal to dA by v by dA by y, and dA by u by dA by y is equal to minus dA by v by dA by x. Now if I find d2u by dx square, that means dA by dA by x of dA by u by dA by x, but that is what? DA by dA by x of dA by v by dA by y. So that is d2 v by dx dy on one hand. Okay. Now this dA by to u by dA by y square is dA by dA by y of dA by u by dA by y. But now I use this, that is dA by dA by y of minus dA by v by dA by x. So this is minus d2v by dy dx. Now I am choosing u and v to be nice functions in the sense that they have second order continuous partial derivatives, suppose. Okay. Then under that condition, these mixed partial derivatives are equal. You have done last year the conditions, maybe in Young's theorem or Schwarz theorem, where mixed partial derivatives are equal. Okay. So d2v by dx dy is d2v by dy dx. So d2u by dx square plus d2u by dy square is equal to 0. Okay. Now u v are such that d2 u by dx dy equal to d2u by dy dx, and d2v by dx dy is equal to d2v by dy dx. Actually the conditions on u and v are second order partial derivatives are continuous. So from this we get that d2u by dx square plus d2u by dy square equal to 0, because here I have d2v by dx dy and here I have d2v by dy. So if you add these two, you will get 0. Okay. And then exactly similarly, if I start differentiating this with respect to y, so if I start with dA by v by dA by y and dA by v by dA by x, then I will get that d2v by dA by d2v by dx square plus d2v by dy square, that is also 0. So real and imaginary parts of analytic function are harmonic. Real and imaginary parts of analytic function are harmonic. Now we will see how to construct analytic function from harmonic function in a suitable domain. So if the domain satisfies certain conditions, then a harmonic function, we can find a other function which is also harmonic, and it is in some sense conjugate to this function such that u plus iv will become analytic. So the method of finding harmonic conjugates we will discuss next time. Okay.